Greetings from Phoenix, Arizona. This is Kurt Marley, your favorite online student, and I am currently resident computer science faculty at Glendale Community College, where I teach university level Java and C++. So besides going to grad school, I've got a full-time job. We're going to be looking at fault tolerant today, this presentation. We'll do a little bit of introduction from your survey just to get us started, and then we'll look at triple module redundancy. Fault tolerance started out as a way for manufacturing to increase their yield to disable faulty circuitry. There's two ways that they do it. The first one is device level fault tolerant. This is where they actually change the hardware, and it's usually transparent to us programmers. It's done at the factory. The other way is a configuration level fault tolerance. This is where you dynamically reconfigure the FPGA away from any faulty resources. And of course, it can be real-time configuration too. Here's a very popular way that they do this at the factory. This is with extra rows and columns. And here you see these segments have extra unused lengths to them. This is how they compensate for having faults. And you see row 3 is defective here, has a defective part. So what they do is they turn on all these unused ends of the segments to jump across the defective area, row, and then they set all their row decoders, they just shift them all down by one. Very elegant solution to get around a defect. And I've seen this done either rows or columns. And here's a nice way that they do it. This is much more robust than just a row or a column. It can get around individual blocks having faults. And we're going to do a target layout, a square closed bracket type shape there you see in the target layout. And the way this works is we've got a little block. It's mostly PLBs. This one has a 4x4, 16 PLBs. And around the top and the left is a block controller. This has a finite state machine, can test all the PLBs of the block, tell whether the block is working or not. And it also has the communication with other blocks. And this is through this little, thick double arrow here is the block controller connection. The way it works is you also have the interconnection block. The way it works is the loading arm, they call it, starts at the block and it tries to trace out the desired layout. And so first we're going to go to the right. That's where we'd like to have another block. But we find a fault there. So we have to back out. We'll still use the connections. We'll pass through the faulty block because we know there has to eventually be a block there on the right somewhere. So we have to back out of this now. And so we extend the loading arm down and we look to the right again. We get another fault. So we got to back that one out. We'll go down. We know we not want a block down there. So we'll configure that block. And we start moving to the right now around the fault, which we can do. That's a nice place for the block to be, the stack of 3 there. And then we work our way up, and if the blocks are all good, we get that configuration. The only thing we've had to do is do the 2 pass-throughs in order to get this configuration. Very nice way of solving, getting around faults. And again, this can be transparent to the programmer. All right, here is the pebble shifting, which is my favorite. Here we have 3 blocks that are bad. 1 and 6 are the ones we want to move to new locations. So what we do is we map number 1. We're going to go from location 1, 2 to location 1, 1. It's going to move to the left. And we want to map number 6, which is in a faulting location, from 1,4 to 3,2. Way down here is the next one. We actually going to move 6 down there? No, we're going to shift everything around in a snaking fashion. So first we move 1 to the left to position 1, 1. And now we're going to move all the others along this red path. And what you do is you do the last one first. Basically 3 comes down to 32. 7 and 8 move left. That leaves 7 free, and then 6 moves down into that space. And by shifting them all in a snaking fashion, you've upset the routing to a minimal amount by keeping adjacent blocks adjacent to each other as you shift everything around. That's my favorite way of doing that. Now, redundancy is an interesting concept. They call it a single event upset, some type of fault that's going to hurt your circuitry. And you do this redundancy because you have something mission critical. It's either machinery you don't want to be faulty or get hurt when something goes wrong, or human beings' lives are at stake if something should fail. And of course, a fault can occur to age, radiation, magnetics, and they can either be transient faults or permanent faults. You can reconfigure around the fault with real-time reconfiguration. And we use these redundant systems every day. Telephone system, your cellular modular phone is a dual redundant system. Automobiles, power grids, military are usually dual redundant. Triple redundant, flight control, autopilots are usually triple redundant or more. Satellites, space applications are usually triple redundant. And CERN is triple redundant. Those beams flying around the accelerator are basically death rays, and they have all kinds of protections. If the beams are going to get out of their magnetic conduits, they can send them to a beam dump area where all that energy can be safely absorbed. No one will get hurt. My favorite is the space shuttle, which was quintuple redundant. If you know your space shuttle history, first mission couldn't launch. There was a software bug. The 5th computer would not sync up with the other 4. It was called the bug heard round the world. So let's look at some triple module redundancy. This is where you have something mission critical, so you triple your application. You have 3 copies of them running. And then usually you have a voter at the end that's going to do a majority wins vote of the answers that the 3 different modules are getting. We're going to do a ripple adder here. And the voter is very simple. It's a basic AND of all the different combinations of 3, and then you wind up ORing the result. You never looked at the truth table for it. Basically, 2 or more zeros is a 0, 2 or more 1s is a 1. It's basically a majority wins type of voting. And if one of them is wrong or something, you can have finite mistake machine to take it, shut it down and do full diagnostics on it and try to repair it. And if you don't remember your digital design, this is a ripple adder with the carry. You can basically put a register after the sums, and I put another register with the output of the voters when I wrote this in Verilog. We did a 4-bit ripple adder. I also did an 8-bit one we'll look at. And there's some interesting surprises we're going to get into. Normally, power is, they try to save power by getting rid of some of the triple circuitry. Here is the Parhi paper that you looked at, and with his ripple adder, he basically only did triple redundancy with the most significant bits. The least significant bits he didn't triplicate, and so he was able to statistically prove that this gives a good result, even in the presence of faults. So, fascinating way they try to save power on these. Basically, it seems like you don't have much people talking about power with the triple module redundancy, which I thought was sad because there's probably some lessons to be learned. It appears that the industry considers it a lost cause. You're simply going to get a ×3 power increase when you have to do the module 3 times. So they usually find out clever ways for each application to remove part of the circuitry in clever ways so they don't have to take a ×3 hit. I'm going to use a 4-bit ripple adder like Parhi did, and also an 8-bit one, and try to find some of the best power efficiency. I'm going to sweep N and see what it does to the routing power and the logic power. And I found some surprises. We'll explore it here. Basically, you know how to do the sweep. You take the 7 parameters, 6 of them get set to a default value, and then we're going to take the N, we're going to sweep it from 2 to 10 and sit and see what happens. I is usually uses this little formula for a I-limited architecture. All right, here's the routing power that I got when we're sweeping N. And you'll see it starts out high, and as N increases, it sort of levels off, oscillates a little bit. There's some stories that need to be researched, why the oscillating is going. I found we had 2 sweet points here at 8 and 16, and you'll see some hints why I think that's happening as we move forward. Why do we have those sweet spots at 8 and 16? And your brain ought to go ding ding, there's something special about those 2 numbers, aren't there? And when I looked at the 8-bit and the 4-bit routing power, I got a surprise. I didn't think I'd ever have the 2 curves cross. And up at N equals 18, they did cross. I didn't go to research that and try to figure out why. Interesting surprise. I did not expect that to happen. That the amount of power of a 8-bit ripple adder would be the same as a 4-bit one out at N equals 18. So now we got to look at logic power, and some complications come about. I'm looking here in the VPR output for an N equals 12, and we should note that the I/O pad in the architecture, the power is set to ignore. VersaPower will not even count the power for the I/O pads, which is a can of worms by itself, we know. An interesting thing is happening. If you look at the VPR output, the resource usage, you see these block counts here, and the net list, our application, is going to want 3 blocks, but the architecture can only give it in a group of 4. Usually it has to be an even number. And VersaPower will greedily count all 4, even though only 3 of them were used, and the 4th one is unused. It gets counted. So we have to figure out how to subtract that off. So here's the dot power. If you never sat and looked at it, there's some good data to be learned here. Here's the logic. The PB types is the basically the logic power. So we have how much power the logic is using, and this is the percentage of total power that number represents. So we're going to have to bonify. We need these numbers. So if we sit here and take the block counts for the CLBs, the net list, the architecture, we take the percentage of power and the actual wattage that the logic used, we can go and correct for it. We'll get a formula here. And when I was looking at this, I noticed something. There's the sweet spots, the 8 and 16. You notice the block count is an even number. It's also power of 2, might be a modulus. There's some research to be done there. How do these numbers interact with the N and the other parameters we're using? So guess what? We got some new parameters we should probably start fooling with, these CLB block counts. So definitely an even number does something sweet Could be a modulus or a power of 2. That was a surprise. So here's how we correct for it. You take a ratio of the net list over the architecture, block count -1, multiply it by the total percent for the logic. Again, -1, you want to subtract it off, and multiply that by logic. We wind up correcting for the power. So here's what we get. Here was the original logic power getting a little high. When we correct it, things are a little lower for the correction. And it pretty much looks like n equals 8 is probably the best compromise for the logic power and the routing power. And it's fascinating that a different n works better for the routing power versus the logic power. And that is a compromise someplace in the middle with n to get both of them a reasonable amount. But we now have the COB count, a new parameter that the CAD systems ought to learn how to take care of and bring into play. We know there's relationships between the parameters. These COB counts, block counts, probably have relationships to the parameters too. So that was a surprise going through and looking at this logic power. The references, the very first reference was the survey of fault-tolerant methods. If you ever find a survey, they are golden. Grab them, read them, study them, and also look at all the references. It's a gold mine.